quick review. The goal here is we want to get to a point where we can do differentiation with natural log stuff. Okay, but to get there, in practice, it's like anything else we do in calculus. It's just going to be a rule that we follow. But to understand where we get this from, we have the tools. We're getting to a point now where we have the tools to kind of see fundamentally and theoretically why this stuff works the way it does. Two things we got to review that we can tie together and we'll make this clear. First of all, second fundamental theorem of calculus, kind of a frequently ignored part of, we don't do a lot with this. We took a little look at it the other day. We remember this. Well, if we go back to it's real simple to apply, but this is the one thing we don't get a lot of traction with this one. If we differentiate an area function, right? So we're taking the derivative with respect to x of this area under the curve f from some constant up to x. Do we remember how we deal with that? Real simple answer. What's that equal to? F of x, right. So all we're doing, remember, because what this looks like, let's take a quick review of this. Remember, if we're drawing an area under a curve, so that's f, and we're starting at some lower constant value, the lower limit of our area function, and we're moving up to x, remember that the area under the curve here depends on where we stop, right? Right? And so what we're able to say here then is the rate at which this area is changing depends on x and not t. Right? All t is there for, if you'll recall, is just to define what the shape of that curve looks like. It's the dummy variable. Okay? But if we evaluate to take the derivative of this thing, we're able to very simply just end up with the function evaluated at the upper limit. Right? And we did some stuff with that. Remember we looked at the souped up version of that. I gave you the handout, the generalized version. But you don't see that very much. I mean, it might show up on an AP test. You might get one question related to that, and that's probably generous. But something that later on in calculus you'll come back to. Okay, so this is the second fundamental theorem. Real quick, let's just practice a couple of those just to make sure we have the idea. What if this is our area function? What if we're looking at something that looks sort of complex like this? We've got a cube root of some function of t, and we're going to evaluate this from negative 17, could be anything, up to x. If I want to take the derivative of that, what are we going to get back? Differentiating the area function with respect to x. So if I want to do f prime of x, it's the derivative of that. What's our little trick? Okay, Grace, any idea? No. Any good? Any good? Well, I wouldn't have to use substitution here. Let me write it this way. Okay, the x is blue. That must be important. What are we doing? Yeah, we're just evaluating it at x. Right. So the answer is, yeah, right. Remember, that's our rule. The x just pops in for the t. That's it. I know you're looking for something profound and hard, but that's it. That's all we're doing. Cube root of x plus 1. Right? That's it. Ought to be harder, but it's not. That's the second fundamental theorem. Okay, how about we could take one that's incredibly hard. Appears to be incredibly hard.
Yeah, that's not too hard.
What about, I mean, that looks awful. We've got a secant to the 99th of some bizarre radical involving t's, and we're going to go from negative a googol. What's a googol?
100 zeros.
100 zeros. Yeah, 10 to the 100. So we're going to go from some, but it's constant. It's a number. We're going to go from negative a googol up to x. That looks horrible, but what's the simple answer to that?
Plug in.
Yeah, all I do is plug in x, right? Okay, so
So good.
That's it, right? Now, that's, like I say, that in itself is not that big a deal, but it's important when we deal with logarithms because remember that when we talk about logarithms, we define logarithms in terms of an area function. Okay, we looked yesterday or the day before at what the shape of a logarithm curve is. If you graph the log function, right? And we all know it's this kind of a starts ambitious, gets lazy, right? Where does it cross the x-axis? 1, good, okay. And more importantly for us in calculus, I mean, that's a, algebra 2, pre-calculus concept, but where do we get that from? Well, this is what we decided was our area function, right? The way we actually derive the value of this function is by adding up the area under an inverse function from 1 to x, right? And that's how we got, remember we talked about how we can get negative values if we take logs of values between 0 and 1, because then we're forced to add the area up backwards and all that good stuff. But what I want to focus on today is how do we differentiate this? Okay, now if the natural log function is defined in terms of this area function, right, the area under the curve 1 over t, from 1 to x, how are we going to differentiate that? Right? Yeah, it's going to be simple, isn't it? That looks an awful lot like the stuff we were just doing. Log of x is an area function. If we want to differentiate this, then we're just going back to what did I just do? What did I just do? That's what I want to do. All right, there we go. So yeah, we're just going back to this second fundamental theorem of calculus, right? Instead of f of t, now we've got this new function that's specific. It's 1 over t, right? We want to differentiate with respect to x this area function. What are we going to get? 1 over x. It's that simple, right? That's the formula, the rule that we get for differentiation of a log function. And if we just go back to that, and it's easy to, now you'll remember it. That's an easy, we use it all the time. But that's where it comes from, theoretically. Now, why do we include this little fine print at the bottom? Okay, good. If we go back and look at the shape of the log curve, it has to be consistent with what a log curve does, how it's graphed. Can we put in a value of x that's less than 0? No. What's the domain of a log function? Yeah, x has to be greater than 0, right? And what's the range? Negative to infinity, all reals. Good. Okay, but we can't, the log function simply won't accept an input value less than 0, and so we always have to have that little fine print on there. Okay, that this only is going to work, obviously, for positive valued x's. Okay, so that's good. That's good. But like all the calculus stuff we do, we don't want to just stop there because that's very specific. I mean, how often are we be dealing with just the log of x? Sometimes. But what if we want to take a log of something other than x? Composition of functions. We can do that. What if I want to deal with the derivative with respect to x of, say, log of x squared, or sine x, or something like that? Well, that's where the chain rule comes in, right? We've got to start with the basic log rule, and we'll push that out and generalize it. So by the chain rule, that's a good review. We haven't done this in a little while either. By the chain rule, how's that going to work? If I want to differentiate with respect to x, log of u, where u could be any function of x, how's that going to work? Now think chain rule, outside in. What's the derivative of log of hand going to look like? What's our rule for that? It's new, but there it is, right? 1 over hand, right? Or u, if we want to call it that. So that's the first link in the chain rule, right? We gotta work outside in. What's the rule for log? 1 over the argument. Okay, so derivative of log hand is, is 1 over hand. Now what's the last part of that? Once I peel that away, I gotta differentiate u. What's that gonna look like? So I've got 1 over hand times the derivative of hand. How would I write that in calculus terms? Well, okay, but I'm not differentiating with respect to u, I'm differentiating with respect to x. Okay, du over dx, sure. And then oftentimes we would just, what do we call that probably in terms of the formula? Make it a little easier, that's too much writing. 1 over u times, what's our abbreviation for du dx? Oh, u prime, sure. And so that's it. That's our general chain rule empowered version of the log rule for differentiation. And really the way we write this in calculus then is the derivative with respect to x of log u is just u prime over u. So you can always think of it as a quotient where the derivative sits in the top and the function, or the argument sits in the bottom, right? Okay, so let's try a couple of these. Let's try a couple of these here. Okay, let's just start off. Why don't you guys start off in pairs and just kind of help each other out? Got a few of these to work through, and then I want you to go do the exit ticket. Do that first before you do anything else. I'll grab you that. So as you're looking at these, you and your partner are looking at these, be thinking about what the u is in each case, right? You want to identify what's the u and then what's the u prime that goes with it. And then, once you've done that, you've got to simplify the result. Just take that first one. Do that one better. I don't know. So what's the u going to be in the first one? 2x. Okay, but the u is 2x, right? Okay. So what's u prime going to be? 2. Everybody agree? 2? Okay. And we know the answer's got to be just u prime over u, so that's no big deal. Just 2 over 2x, which simplifies to 1 over x. Okay, now, is there a way, take a look at that one real quick, is there a way that we could have maybe pre-written that log? It was fine the way we did it, but could we have simplified the log using, remember we talked about ratcheting the arithmetic operations down? Say it again. Ah, okay. Yeah, so we could even do this, couldn't we? We could say the natural log of 2x before we even did the calculus. What's our rule for the log of a product? Okay, sum of the logs. Good. Okay, so that's log of 2 plus log of x, right? Now, what if I differentiate that? what's the derivative of log 2? Okay, 1/2 times 0, but do we even need to do the 1/2 part? What is log 2 after all? It's some number. It's just a number, isn't it? It's just a constant. So what's the derivative of any constant?
0.
0. Sure. Right? So when we differentiate, this guy's going away anyway, right? And this just sort of devolves to the derivative of natural log x, which is 1/x, right?
Yeah.
Okay. Which is better? I don't know. I don't know, maybe the top one was even fewer steps in this case.
Yeah, but you can know that if you have two terms and one of them's a constant, then you can just go straight to x.
True.
So it's knowing that
You can. And the other thing too there is, it opens a door for us. What if we had something that was really complex? You know, what if we had a product of complex things and powers combined? Well, you can see that perhaps then you start to get to a point where maybe you do want to use those properties of logs to simplify things first and then push into the derivative. Okay, try the next one. Try the next one. You can work on your own if you want. Feel free to work with a neighbor. It's going to get a little harder. Pick a U. Pick a U prime. Now, one question before we do the next one. We had some freedom on the last one to either use the properties of logs or not. Is there a property of logs here that's going to? Oh, people are shaking their heads.
No.
How come? What?
You
You can't go further than the bottom rung. Okay, so we can't. There is no property of logs that helps us with a sum, right? So this time we don't have a choice. We just have to use the rule. Okay, so have at it. Here you go.
Did you have long?
Nope. Once you get it down to simplified form, I mean, if you can simplify, that's great. Okay, so what's our U?
plus 5.
X cubed plus 5. Okay, so on this guy we can pick U equals X cubed plus 5. So what's my U prime?
Or 3x squared.
3x squared, power rule, okay? So what's our answer then?
1/x plus 5.
Okay, and let's just stack them up so the U, we'll just put U prime on top and U on the bottom. So 3x squared over x cubed plus 5. Can I reduce that out directly? Or simplify it? No, I can't. So that's it, right? That's what we get. Now, how would we do something like this? This is a little different. Take a look at this. Nobody answered yet. Everyone stare at that for a second. What's going to be our approach here? We're differentiating like this different animal. Yes, sir.
Differentiate the x and then at the end you multiply the x with 2.
Say it again.
You differentiate the x, so.
Meaning the x.
The natural log. The natural log.
Oh,
So then 1/x and you multiply the x with 2.
okay. What about, but that x squared, that's a function of x. What do we do? Let me ask you this. Let's think back to, and the reason I think this is, you guys are looking for something, you're looking for a property of logs to bail you out here maybe, but what would you have done, let's go back a little bit, what would you have done with something like this? What if we had, say, y equals x squared times sine x, and I wanted to find y prime? What rule do I have to apply first there? Product rule, right? How many factors are there being multiplied together? 2. What are they?
X squared and sine x.
X squared and sine x. Okay, so let's warm up with this one, and then we'll move up to the log. So if I use the product rule, what's that going to give me? X squared cosine x. How'd you get? Because we're using the product rule being one factor times the derivative of the other plus flip it, right? Okay, so x squared cosine x plus, okay, plus sine x times derivative of x squared, which is our 2x. Okay, right, and then we could just combine things if possible and factor and all that good stuff. We can simplify maybe. But what about here? What's our product?
X squared times natural log x.
Okay, so we got two things. We got x squared, and then we got a log x, which we're now equipped to differentiate, right? So what are we going to get?
X squared.
Okay, good. X squared times the derivative of log x, which is 1 over x, plus
2x natural log.
okay, log x times derivative of x squared, which is 2x. And if I simplify that, what are we going to, what can I do over here? Okay, plus, how would I probably want to write that? And remember, we're kind of really, mathematicians are really picky about this stuff. How do you suppose I'd want to write that?
2x.
Ah, okay, good. Yeah, good. We want to put the constant first, then the x, then the log x. That's it. Okay, that's it. All right, I think we're getting this. I think we're getting this. Now, what about this guy?
What is?
Now, I want you to think about this. 90% of the calculus is not can you do the rules? Can you do this the smartest way? Can you do this the easiest way? So think about your options here. Ah, okay, yeah. If I just try to blindly apply the log rule to this, well, actually, hang on here. I see what you're saying, but I'll trick myself. Now, can I use a log rule here?
Oh no, it's outside.
Ah, okay, it's different. I actually can't. I actually can't. Now, this is different from, watch this. This argument here is different from the natural log of x to the 7th. You see the difference? Now, what's the log rule that would apply here? Okay, log of a power ratchets down to a product, right? And so this becomes 7 log x. That would have been nice. That would have made things easy. But that's not what this is up here, is it? No, this is a composition of functions, and this is a log on the inside and a power function on the outside. So how do we have to deal with that one? Chain rule, yeah. So what's the outermost function here?
Hand to the 7.
Okay, to the 7th, a power, right? So I've got hand to the 7th.
7 hand to the 6.
Okay, so if I differentiate that, good, I'm going to get 7 times hand to the 6th. The hand is a log x. So the derivative of hand is 1 over x. So I could combine those to what?
7. 1.
Okay, so 7, see, 7, okay, put the x on the bottom.
1 of the natural log x. 6.
Yeah, can't do much with it. Okay,
What if you put in your calculator?
what if you say it again?
What if you put it in your calculator?
In what way?
Yeah.
Oh, it's gonna, what's it gonna look like?
Yeah.
It's a good question. It's gonna stretch it out a whole bunch. Okay, what about this guy? Could we, that looks terrible, but this time, could we maybe bail ourselves out a little bit?
Yeah.
Ah, okay.
One half element. Yeah.
Okay, yeah, if we rewrite this in terms of an exponent, what's that square root gonna become?
1 half. So 1 half coefficient in front.
Natural log of 17x to the 1/2. Okay, now we can do a lot with this one, can't we? Good, okay, step 1, we can take the exponent down front, then what?
Ratchets down to addition.
Ah, okay, then I've got a log of the product, right? Okay, so that's helpful, we got some good stuff here. So we get the derivative with respect to x of 1/2 times,
Natural log of 17 plus natural log of x. 17.
okay, does that make sense?
Yeah.
Okay. And And then now if I differentiate that, I got two terms. What can I do with that 1/2 if I want to?
Leave it there, pull it up.
I could pull it out front. It's a constant multiplier, so I could even pull that out of the whole derivative, right? And if I differentiate these two terms, derivative of log 17, 0, right? That's a constant. So that goes to 0. Log x. Yeah, so I just get 1 over 2x, right? Okay. All right, so I want to get you down to the lab. Real quick though, before we go, I want you to just think about something like this. Any ideas here? And this is a topic for next time. But any ideas? There are no logs in that, right? No natural logs. Any ideas how we could maybe figure out how to differentiate that without driving ourselves nuts? Google it. Okay, I get an idea here. Yes, sir. What would happen here? Just hypothetically here, what would happen if I took the natural log? The natural log of both sides, right? Okay. So on the left side, I'm going to get a natural log y. Now, if I differentiate, that means I'm going to have to differentiate implicitly, right? We're going to have to just, instead of differentiating, I'm going to have to differentiate everything with respect to x and use the chain rule to get my y prime on the left. We'll review that stuff a little bit, but we've done that before. But look what happens to the right side. So the left side gets slightly more complex, slightly. But what happens on the right side? Instead of having these three factors, I've got this complicated cube root of x and this 2x minus 3 and this square root on the bottom. What's going to happen to all those factors? Okay, I've got a product on the top, so I'm going to get this guy plus the log of that guy plus the log of that guy minus the log of that guy. And even looking individually at those players, they're going to get better too. Because if I focus just on him, how could I rewrite that in a way that's going to help me with the log? Yeah, okay, x to the 1/3. Pull the power down, right? This is looking easier all the time. These are going to be easy logs. This one I'm kind of stuck with, aren't I?
Yeah.
But this guy down here could be a 1/2 power, right? And so I'm going to get much, much easier stuff to deal with. How much time, now imagine what that would be like if I had to use a combination of the quotient rule with the product rule with those individual power rules nested in there. That doesn't sound like a lot of fun. That's several pages of work. Now, it's too late for me. This is what happens if you don't use logarithmic differentiation, but I can save you the... See, I didn't do that. Look what happens.